Okay, so this is just going to be a quick intro to the Hyperdrive repo. Hyperdrive is the reference implementation of a hyperware runtime. So we expect and hope that in the future we're going to have other implementations of the hyperware runtime. For example, you could imagine just implementing it in a different language. You could imagine implementing it entirely in the browser. But for now, there is one implementation that is Hyperdrive. And so this is just going to be a walk through the repo to kind of give you a sense of where the sort of big pieces are, how they connect, and just a kind of, top level overview. So if you wanted to dive in and, make changes to net or to a specific package or perhaps even the kernel, you would know where to start. So, mhm. The second thing, yeah. So ultimately, we do plan to, you know, make a specification of what the hyperware runtime or a hyperware runtime should do. We haven't gotten to it yet, so this is kind of, the thing. But certainly, we would like to do that in the future. Okay, so just like here's kind of a hopefully readable diagram that I put together to just kind of show how the hyperware runtime, the different pieces of the runtime itself. So you have this big box. This is a node, and then you have other nodes that your node can talk to. And a node is just a instance of Hyperdrive. You've got everything is sort of talking through the kernel event loop. So we have a message passing system where we have this event loop that everybody is going to talk to. So we have this kind of microkernel architecture. And then we have a number of what we call runtime modules. So here I have, for example, the VFS, the virtual file system. We have an HTTP runtime module, net, and ETH. And so these guys are native code, and they're basically the things that we had to write in native code because we couldn't write them in WASM. I'll come back to that in 1 second. But the user space processes are another thing that send messages to and receive messages from the kernel event loop. These are, we refer to them as processes. These are WASM components. So that's a specific type of WASM module is the terminology. Sorry for some of the overlap here, runtime module, WASM module, but it's a WASM binary that has specific calling conventions that allow you to do, like, for example, like typed calls into and out of the WASM binary. That's kind of mhm. That's right. Yep. Yeah. So, for example, like a WASM component defines a WIT file, WIT, which I think is WASM interface. I don't know, something like that. But it's a way of defining the interface in a language neutral way, and the kernel is responsible. In addition to running this event loop, the kernel is responsible for starting and stopping user space processes. It's also responsible for furnishing these user space processes with certain functions. So, for example, it give it the kernel defines a way for these processes to receive a message from the event loop or to send a message to the event loop. So you don't have to go and implement that in a process. It's just a function that you can call. So there are certain limitations to these processes. One of which is they can't really talk to the outside world much. We've got it pretty locked down. So if you're familiar with WASM components, you'll know that there's this. So right, there's kind of this multi-level scaffolding going on here. There's WASM, which is very sandboxed. Then there's WASI, which is giving WASM modules the ability to do things like write to your file system. That's right. And in general, we don't allow hyperware processes to do things like that. Instead, what we do is we use our, for example, VFS. In the case of writing files, for example, we would use our VFS, and your WASM process would send a message to the VFS. So it would send a message that would pass through the kernel event loop to the VFS. Then the VFS would handle writing the file. So the VFS is native code. It can just do things like Rust's standard FS write or whatever. So if we're talking to the outside world, it usually happens through a runtime module, as opposed to through WASI, and that just gives us more control over who can write what, who can talk to who, and so on. So everything is always just passing a message, as opposed to using a WASI type interface. That's right. Yep. And then kind of the final thing, I mean, I mentioned that the kernel furnishes sort of these functions that user space processes can call, but the final thing to kind of mention here related to the kernel event loop is that we have these this CAPS oracle, capabilities oracle. So there are, we use a capabilities security model where different processes or modules can possess a capability to, for example, send a message to another process, or just to give a couple more examples, to send a message over the network, the hypernet, or to write a file in a specific drive, or read files in a specific drive. So the way that ends up working is that and there's some subtlety here. I'm not going to go into details right now, and maybe we can come back and talk about it more later if there's interest. But your app, say App Store, would have this capability to say message VFS, and then when you send a message, when you try to send a message from App Store to VFS, then the kernel is going to enforce whether or not you have the capability to message. So let's say you didn't, then that message will just drop. If you do, okay, then capabilities oracle may be consulted, and then we'll go and do VFS stuff if you pass muster. And then, sorry, go ahead. Mm-hmm. Mm-hmm. No, it's a good question. Yeah, we can talk about it right now. So the main one that comes to mind is, and maybe let's go away from this diagram. Well, yeah, okay, let's not. We can go look at the code later, but the main one that comes to mind is user space processes have the ability to write to a temp directory. Each process has its own temp directory. I don't know that we're going to keep this feature, because the problem, like I was kind of gesturing at earlier, the problem is we don't have a lot of control over this in the sense of, like, what happens if you download a malicious process that just writes zeros to temp forever in a loop. Then you're going to quickly run out of disk, and Hyperdrive doesn't have much ability to stop that, right? As opposed to the case where you can imagine, we don't have a lot of capability to stop that right now through VFS either, but that's right. Yeah, so so that's like, that would be like future work. So yeah, so not certain that that's going to stick around just because of the sort of that issue there.
Yeah. And in general, though, the goal is for user space processes to be as to do all their work basically through communication with through the messaging system.
That's right. Yep.
Okay.
Yeah. I think I realized I didn't have your audio coming through to the recording until now, so that's unfortunate. We'll have to like annotate later, but that's fine. I changed it now. We'll just keep going. Okay, so the final, so one more thing to talk about for messaging before we start looking at code is, messages are designed in a, like, so our project is certainly inspired by Urbit, and one of the things that Urbit got really right is that a message to something that is running locally looks the same as a message that is to something that is remote. So what I mean there is, when you send a message, so let's say App Store is sending a message. Let's say App Store is sending a message to the local VFS. Then you're going to specify, so this would be a request. This is actually something I need to talk a little bit more about as well, as request response. But this would be a request. A request must specify a target. And so the target would be your local VFS. I'll show you like what that looks like in a moment. But you would specify a request with a target local VFS, and then it would just, go, check your caps, go send it to VFS. VFS responds, and now responds with a response, in fact, and then that goes through the event loop back to the App Store. Let's say that instead of doing a local request, now let's say that App Store is, for example, downloading an app over the Hypernet. App Store would create a request with a target of some remote node's App Store, would send that message to the kernel event loop. The event loop sees, oh, this message is not local. This message is outbound to some remote location. It will send that message to net, which is our networking, over peer-to-peer networking runtime module. And net will then go and send that over the network to some remote node. So there's a couple things to talk about here. One thing is that net is the one who is responsible for giving you a negative ACK. So like, let's say that you try to send to somebody who's offline, or maybe your connection is just really bad, or their connection is really bad and it times out. Net is going to issue you a response of a send error. So you can then, in App Store, you'll get a response through the kernel event loop to your App Store app that will say, send error with some sort of information, like, is it a timeout? Is it a is the node offline? And then you can handle that however you want, right? So in some cases you might want to do a retry, some cases you might want to just bail, but that's up to you how you handle that. There's no ACK if it's successful, but oftentimes your protocol will specify some sort of request response. So in the case of downloading an app, the logical sort of response here is going to be like, hey, here's either like the entire app, or here's like a chunk of data, and then I'm just going to keep passing you chunks until we're done. So that would be kind of in place of an ACK, would be a response from that remote App Store, who would in turn send in this case, a response message to their event loop, it would be routed to net. Net would route it back to us, and then through net to kernel event loop to App Store.
Okay. Yeah, I've definitely seen this, taking a close look at the full event loop logging and stuff, and seeing what you were saying as far as being like a completely like standardized structure. Like, okay, I might be my first message might just be from the terminal
Mm-hmm.
to a different process, with the target still being my node. But then maybe if I was hiring somebody else, some other node somewhere, then that would wind up eventually becoming a message that that targets net, which then will target the external node or something like that.
Mm-hmm. Yeah, and definitely like looking at the full event loop is super helpful to understand how these things flow. So would be highly recommended. We'll try to remember to like just show like a quick preview of like what that stuff looks like.
Okay, and
Mhm.
request and response, they're specific message types, but they're not the only ones.
So they are specific message types, and they are the only ones. So yeah,
They are the only
this is
ones.
something.
Okay, that's always
Mhm.
got it.
Yeah. Yeah, this is definitely important to cover as well. Excuse me. Yeah. So there's two types of messages. There's a request, which you specify the target for when you create that request, and then you can also specify when you create the request, do you expect a response or not? And then there's a little bit more complexity here, but that's kind of the main thing that you can do is you can say, do you want a response? And then when you receive a request, you have the option of sending a response. You do not specify the target of response. The response will be routed by the entirely by the kernel. So what that means is that we do a fair amount of logic to do the correct thing, whether it be over the network or locally, and it also means that like let's say that you have to set up your protocol properly. So like let's say that you send a request but you don't expect a response. Well then you will not like we're not going to route a response to you, right? But there are cases where like you can maybe it's time to draw. Let me pull up a drawing app real quick here. Okay, so let's say process A sends a request, which I'll denote Q, to process B. Process B can then respond with a response, and so if Q is expecting a response, then S will just get routed back to A. Okay, that's like the simple case. You also have a more complicated case of A, B, and C, where let's say A sends a request to B, and then in order to fulfill that request, B has to consult with C. So now B could send a further request to C. You can imagine like there's a couple of ways that you can imagine a response propagating here. So like if let's say A's request to B is expecting a response and B's request to C is expecting a response, then when C sends a response, it will get routed to B, and then B can in turn respond and it will get routed to A. Now there's another case here where maybe we want to skip B in the response, so we don't want to like daisy chain all the way back. We just want C to respond directly to A. So in that case, if A sends a request to B expecting a response, and B sends a request to C and does not specify that it expects a response, if C responds, it will go all the way back to A. So there's a sort of like I said, we do a fair amount of logic here to try and do the right thing, and to also like be as efficient as possible, so we don't need to like daisy chain through a bunch of you know, a bunch of different processes that don't actually care about the intermediate result. I don't know that we're going to go into depth on this, but yeah, it is something to be aware of, that we do this sort of routing for requests and responses.
Is this in fact related to like to routing itself? Like if you need to work indirectly or through a NAT or something, or is it just am I just seeing a logical similarity to that?
Not sure. Can you say more?
Yeah, sure. Like if I'm an indirect node,
Mm-hmm.
and and my router therefore doesn't
I
really,
see.
care too much about the specifics, just wants to get the request to me,
Mm-hmm. Yeah, I see.
and my responses then will can go back to the originator.
I think we do not do this, but this is something to look at the code about. This is more like, I think this is more, well, no, I think it will work over, it will work over the network, but I don't think that we use it for that case, no. Because ultimately, if we're doing an indirect node routing, we're going to have to like bounce stuff through, we're always bouncing stuff through that node, I think. Yeah.
Interesting. Okay.
Okay, so that's just a little aside on request response. If there aren't any questions about this stuff that we just talked about, then I think I'll just kind of like do kind of a quick tour through the code, and we can point out some interesting things and go from there. Any other
Great.
questions?
Not for me. All set.
Okay, cool. Yeah, so let's take a look at the code. So I'll just be clicking through here in like the GitHub interface. Let me zoom in a little bit. So the repo looks like this. We have a number of directories. Scripts is going to be stuff like for building, right? So building. Oh yeah, I didn't tell you about packages. Okay, let's talk about that briefly. So, excuse me, I told you about processes, right? User space processes. So something to understand is that so the kernel sees processes. The the App Store sees packages, and a package is just a collection of one or more processes and possibly front ends. So if you, what we'll see when we're looking at these user space processes, which are actually packages, these collections of processes, is some of them are just one process, and some of them, like App Store, are actually a collection of multiple processes, and then also like a front end. So yeah, so that's what I mean when I'm talking about a package. Okay, so anyway, so in scripts we have, we can build the sort of user space packages or processes, and then also like build releases and so on and so forth. Then we have the sort of main directories of interest are Hyperdrive, lib, and source. So source is just kind of like a stub. So this is the reason we have this directory structure is because we wanted to be able to import the types of Hyperdrive. So that's sort of what this source is doing. Lib here is just the types. So if we go and we look, we're going to see a variety of different types. We have our core types. This librs is just sort of re-exporting everything, and then it's doing this WASM component related code gen, binds gen here. This will be important later. but yeah, I mean, so this is where all of the core types live. So we have, like I said, core. We have HTTP. So if it's a type, it's going to be defined here in lib. And then Hyperdrive. This is kind of where all the code lives. So we have all of our runtime modules and kernel live in source, and then all of our finger quotes user space stuff lives in packages. These are like all bundled with the Hyperdrive runtime, but these are all WASM. So if we look at this, well, let's kind of go from how the runtime actually starts up, and then from there we'll maybe look at the kernel. We'll maybe look at maybe one or two runtime modules, and then we'll look at a process or two, depending on how time goes. But yeah, so main. This is where things. This is what happens when. This is kind of the entry point when you run the runtime. Let's see here. So we have our main function. So let's see. What's worth pointing out here? We do a bunch of setup, and then what's one thing that's worth discussing is we have right. So you can see here Tokyo main. So we use this async runtime called Tokyo. We do a lot of multi-threading and parallelism type stuff, and Tokyo kind of gives you an experience that, if you're familiar with Golang, should be pretty familiar. So they call it a Tokyo task. A Tokyo task is like a Go routine, or if you're not familiar with Golang, it's like you can. The intuition is it's like a thread, but it's a little bit lighter weight than a thread. So there's some implementation details that make it a bit lighter weight. But we do a lot of communication between these different Tokyo tasks. You won't see this in user space, but if you're building on the runtime, you'll see this a lot, where we have these Tokyo MPSC channels. So these are the right. There's kind of two main ways that you can communicate between threads, or in our case tasks. Right, one is shared memory, and the other is channel. So we do a lot of so basically all communication between, if we're looking at these arrows, this is all over channels, and then we do shared memory, but it's almost I think it's, if not entirely, it's almost entirely within a module. So for example, VFS will have some shared memory. It will itself spawn tasks when it's handling requests from the event loop, and so that's where we would use shared memories within a given module. But all communication between modules and between processes, it's all channels. And each of these processes and each of these runtime modules is running on its own task or its own thread. So this is just setting up all the different channels. And then I'm going to kind of scroll through here to get to the interesting part. Yeah, okay, so here we are spawning all sorts of different runtime modules, right? So here we're spawning the kernel, we're spawning the networking, our state. We have a couple ways of preserving state, but one of the ways that we offer is, writing to disk. It's not directly to disk, it's like to a key value store, so you get sort of like atomicity and stuff. We provide a number of these, so these are all just different runtime modules that we provide: VFS, file system, ETH for talking to the blockchain, HTTP server and client, and so on. Okay, so this is kind of the entry point where each of these things is called, and so I think probably going to go look at the kernel unless you have any questions about this main or anything that I've said now.
I guess the only thing I'd want to ask is then, am I correct in like the way I'm kind of seeing similarity to Urbit then, with the main modules being the being a lot of the vanes that are instantiated at at boot time, and with the user space processes basically being the gall gall apps in that sense that they've got they all kind of use a standard way to communicate to the individual vanes. Then
Yeah, certainly. Yeah, we're definitely heavily inspired by Urbit. I mean, we definitely pursued like a very sort of microkernel approach. I I don't know. It's been a while since I thought about the details of like the Urbit kernel, but I think our message passing system is fairly different. And of course, we use WASM, so we're using something that's kind of like for our user space fundamentally different from our runtime modules, or as Urbit would call them, vanes. Uh, but but yes, certainly there's some significant similarities there. Yeah,
okay, thanks.
yeah, sure thing. Okay, so let's take a look at the kernel. So we're going to go to source again, Hyperdrive source, and then we have this kernel directory. So we have these kind of three files here, mod, process, and standard host. So so the kernel, as I said earlier, is responsible for process process lifecycle, starting up, tearing down, etc., and the event loop. So if we look at, I think it's event loop. Let's see here if we can find it. Yeah. Okay. So kernel. Yeah. So this guy got called, if you recall, in main. Yeah. So it got spawned as its own in its own task, and so kernel, as the comment helpfully supplies, contains the event loop, which handles all message passing between all processes. So there's a bunch of setup that happens at the start of this function. But then, if we get into it, we have this loop. Here's the event loop. So all that this guy is doing is, right, there's some like debugging stuff here that's useful for devs. But all that this guy is doing is, so a Tokyo select is basically saying, I'm going to listen on these different async channels, and then whichever one I hear from first, I'm going to like execute on that message. And so like here we're listening, for example, on network, or for network errors, we're listening on this channel receiver, receive and loop. So we'll see how we send a message from a process, but we receive messages always on this receive in loop. And so if we hear a message, then we go and process it, right? So we can do things like we can see, is it from our node? Is it to our node, right? We can check capabilities. Here are the special kernel level capabilities checks. So this is like, do you have the ability to message this process? And then just scrolling past a lot of stuff here, capabilities checks. We have kernel requests themselves. We'll handle those. So that's like, I was saying process life cycle. So like, is this a request to start a process, or is this a request to kill a process, for example? If it's not a kernel request, then we're going to get a sender, the sender part of a channel, and then we're just going to put the message onto that channel, and then like send it off, right? So you can think about it as like each process or each runtime module has like a little mailbox, and then the event loop is just like it's like, I don't know, just like getting all the messages and then sorting them into the proper mailboxes. And then here's the CAPS oracle that I was referring to. The CAPS oracle is another one of these possible things that we're selecting over. And this is just going and doing all the checking, like, is this cap actually like real? Are we adding a cap? Are we whatever? Okay, so that's kind of the event loop at 5,000 feet. Any questions about that before we move on to other kernel stuff?
Yeah, the capabilities that are being checked, they all
Sure.
refer to all refer to module operations. Is that right? And it's a matter of whether or not a given process can actually access that in one form or another.
So there's kind of two classes of capabilities. One class is, I think it referred to them above as like special. Yeah, okay. So the special kernel level capabilities are messaging and networking. So networking is just like, can you send a message over the network, and can you receive messages over the network? So if you get a message to your process that does not have the networking capability from a remote node, the kernel will not pass you that message. Similarly, if you try to send a message over the network and you don't have the network capability, then the kernel will not send that message. And then messaging is similar, except it's just like, can you even message this local process? So these ones, when you write your package, here I can go and actually show you rather than just talking. So I'm going to jump over to just for this quick caveat to Hyperdrive packages. So this is where the runtime packages live, and we're just going to look quickly at let's look at App Store. So App Store, this is kind of an aside, but without going into too much detail, each of these directories, there's certain special directories, but if it's not a special directory, it's a process. So like App Store here is a process. Chain is another process within the App Store package. And then PKG is one of these special directories. So the PKG directory is what is going to contain, when we compile this package, it's going to contain the binaries, it's going to contain the compiled UI. And this is what, if you were developing a package and then, starting it on a node, the PKG directory is what's actually uploaded and given to the App Store. It includes in it this manifest.json file. Manifest.json is where we define what processes do we want to run when this package is started. So here we have a bunch of different processes that are started when the App Store package starts. And you can see, in addition to like the various metadata about like, okay, what's the name of the process, you can see this request networking field and this request capabilities field. So when you request networking, the kernel will then give you the capability to network. When you request just a process, oh man, okay, we're gonna do a caveat within a caveat. Sorry for the nesting caveats here. So this thing here, chain app store sys. This is a process ID. It's 3 parts separated by colons. So sys here is the publisher. In general, this is going to be a node. So like if I were publishing from my node, nick.hyper, this would be nick.hyper. There's a special one, which is sys, which is the things that we're packaging into the Hyperdrive runtime. The second field from the right is the packet. The package. So in this case, this is published by sys. The package that it's published within is App Store, and then the process is chain. There's one more field that we would specify to have this fully specified, which is the node that it's actually running on. So if we were running this process on nick.hyper, it would be nick.hyper at chain : app store : sys. And that would fully specify how to. That would be the target. For example, if you were sending a message or sending a request to my chain app store sys.
Is the process name required unique across globally on a node or just within the package?
just within the package. So that's why, yeah. So when you fully specify this four field thing, then you have a sort of globally unique identifier for each process. And
Got it.
then here, what we're doing. So that nested caveat is over. What we're doing here is we're specifying the local process is implicit, but we're specifying I want when I boot downloads, I want it to be able to have the messaging capability to chain App Store sys. So when downloads starts, we will make sure that the kernel will say, oh, okay, I'm going to make sure to give the messaging for chain App Store sys to downloads. So downloads can now message chain App Store sys. When we're starting these packages that are bundled with the runtime, these are just handed out, right? If you are downloading an application and installing it, there will be a prompt in the App Store that says, hey, this process downloads is requesting messaging to chain App Store sys, and then you can say yes, no, right? So let's say you download some sketchy application that claims to be, I don't know, like a timer, but then it's requesting, I don't know, like root capabilities to write to the VFS. Probably don't grant that, because if you grant that, now it can go and write and read arbitrarily in the VFS. And this is kind of the way that the user ultimately has some control over packages' ability to do stuff on their system.
Yeah, I'm assuming it's for a given package. Then it's take it or leave it, right?
That's right.
You either give it permissions, or the permissions that it says it needs, or you don't.
That's right.
You don't. This doesn't actually get edited.
That's correct.
By user.
Yeah. And so we've talked about in the past, like, would it be nice to have the ability to, like, I mean, so like if you imagine your phone, oftentimes you'll install an application and then, I don't know, maybe you do some function on the phone, like maybe it's a bank application and you're trying to deposit a check. The first time you try to deposit a check, it will ask you, oh, do you want to grant the ability to use the camera to this application? So it's not when you install it, it's when you actually use the feature. That would be pretty nice. We don't currently have that, but that's kind of a possible feature that we might want to add in the future. But for now, it's when you install the application, it will give you a list. Hey, here's all the capabilities this thing is requesting. Do you want to grant these? Yes, no. No
Nice
implies
to have
don't
both.
install. Sorry.
Kind of nice to have both. Nice to have both, and know exactly what the application could potentially ask for in the future, but know that you don't have to grant it just to run the most basic features of the app.
Yeah, that's true. That's true. Yeah, so maybe you could yeah. Anyways, future work. Okay, so going back to so now we're out of the initial caveat. Capabilities. So back to capabilities. There are special kernel level capabilities which include messaging and networking. So those guys are handled kind of separately in their own thing here. All the other capabilities are defined by runtime modules or user space processes. So to give an example, the VFS has a model of the VFS model is that a process can create a drive. A drive is just like a top level directory. Let me actually show you. Okay, so here I will show you what it looks like. Where do we want to go? Hyperware Homes. Let's look at Diligence OS. So this is what a node home directory looks like. we have the kernel stores some files, and then we have the key value store in SQLite, runtime module storing some files. We have a variety of these dot files for specifying, things about the node, as well as some terminal logs. And then we have VFS. So if we go into VFS, each package has its own directory. And so if I go into, for example, what's going to be a good example? I think App Store will probably be a good example. So if we go into App Store, we're going to see that App Store has these three, or so it has these three different directories. The temp directory, which we kind of referred to offhand as this is the thing that WASI can write to and that we might remove. PKG, this is where, we saw just a minute ago, like manifest lives. This is where all the WASM binaries live. The API lives here, our UI, and so on. So PKG is always there. TMP is always there, may not be in the future. And then other directories are what's called drives. I mean, I guess PKG these are also drives, but these top level directories within a package directory are drives. And a drive, so here, downloads in App Store contains different apps that have been downloaded over the network. But each drive has capabilities associated with it. So when you go to the VFS, or when you talk to the VFS with your package and you create a drive foo, that will be created inside of your packages, inside of your package directory. It's this top level thing. It would be called foo, just like how we have a PKG or downloads here. And you would be granted read and write capabilities. Your process would be granted read and write capabilities to that drive, foo drive. And now you can go and do operations within foo. You can read files, write files, provided that you have the write capabilities or the read capabilities. And you can also share those capabilities with other processes. So now maybe your application, you want to have another application that can, edit files within a certain drive. You can grant write capabilities or read capabilities to another application, and now that other application, that other process or package, can go and do those read or write things depending on its capability within that drive.
Okay, so extending the iPhone metaphor, then, if you could, much like you may have been, you granted the app the ability to access the camera. In this case, you could let other processes potentially access your drive where your photos are stored, so those could be used in other packages.
Exactly, and this is arbitrarily programmable in the sense of like we give you the kernel gives you the ability to create capabilities and check that capabilities exist on a given message, or that a given process has a capability, but you have the ability to program like what is that capability, what is it for. So the drive is just one example. Another example would be like the contacts app. And I realize I am being a bit sloppy with my terminology here. When I say app, that's pretty much equivalent to package.
Yep.
Yeah. So the contacts package or the contacts app has capabilities associated with, are you able to read certain data on a certain contact? So you can very granularly say, I want this application to be able to see who's in my contacts list, or I want this application to be able to see, not just who's in my contact list, but all the information associated with that contact. So you can specify arbitrary fields. You can say, the name or the address or whatever. I want this application to be able to read that data, or I want it to be able to write that data, right? So these are just some examples of capabilities, but that's it's you can program it to do whatever you want. One thing to say before we move on from capabilities is that the capabilities, so the kernel will ensure that capabilities are correct. So if your process is asking, or let's say that your process defines some capability, and let's say that a third-party process running on the same node is asking to do something that is gated by a capability. It cannot be spoofed. The kernel guarantees that the capability is real if the kernel passes through the capability with the message, then it is real. So it's like a field in the message that you receive, in the request or response that you receive. Now, there's a tricky bit here, which is that capabilities should only be used for like local processes. So the reason that I say that is because the assumption, so the kernel will also guarantee that you only, so if let's say your app gives a capability to some other app locally, the kernel guarantees that that capability does not leak to other apps. Now that other app can go and give that capability to other things as well, right? But the reason that you can not trust a third party, that you cannot trust a remote node with a capability, is that you have no such guarantee for the runtime that remote node is running. They could be running a hacked runtime where that capability is just available to all processes. So even though they're running a legit process, even though that doesn't leak the capability, the runtime itself may have been modified to just give the capability to arbitrary processes. So as soon as that capability, so the intuition here is do not use capabilities for stuff that's over the network. You're going to want to use capabilities only for local, and then over the network, the best you can do is confirm a node identity.
Yeah, that was just kind of how I was going to put it. Like for the over the network, you have it's trusted as far as identity is concerned, but not as far as capabilities.
That's right. Yep.
Okay. A quick question
Sure.
about the okay. So obviously, messaging and networking are in their special category because they are they are they're implicated in being able to interact with the event loop itself, as opposed to the other ones that are not in the special category. Are they dynamic, or are they all statically specified in? I guess what was it in the manifest, or can they actually change during the lifetime of a package?
Yeah, good question. The special kernel ones are static in the sense of they're granted at the start and that's it. At package start time. The other ones are dynamic. So you can grant or revoke or whatever. And there is actually there is a bit of a weird behavior here, which is that there's some room for improvement here in terms of like sometimes capabilities get a bit wonky if like a package if you reinstall the same package in terms of like are old capabilities still good for that package.
That's kind of what I was wondering. Are they stored in? Is that dynamic version of them like? Is it queryable? Is it stored in memory? Is it persisted?
We're getting to the edge of what I can say off the top of my head. I think I have observed behaviors where, for example, I reinstall an application, and then that like other things will not be able to properly message that application in some cases. So like the capabilities are not, being updated properly. But yeah, in general, the idea is that it's static, it's at package start, and that's kind of the way it is.
Got it.
Something. Yeah, I think there might be room for improvement here for that specific thing. Okay, more questions on capabilities or event loop stuff?
Oh, and yeah, the one aspect of that was just wondering if they were queryable, do you only discover them in failure?
Specific to messaging and networking, or specific
No,
like
no,
broadly?
specific to the non-special ones.
I believe that you can find out which ones you have. I'm just going to jump over to the process lib here. The process lib is, this is a set of library functions that we expose to WASM processes that will make your life a lot easier, and we would strongly recommend that you use these functions. We wrap over a lot of the messaging so that you don't have to interact on kind of like a low level. So let's go look at.
And I imagine this is where you'd know what other processes were actually running on your nodes from from a different process.
Yeah. So interestingly enough, I think you cannot know that without actually going and like trying to hit that process. Like there's not like a list, like a directory of like, hey, here, here's the yellow pages of what's running on the node. But okay, so capability. So this is a just kind of like wrapper type over capabilities, and I think we can query. Okay, maybe no, I'm looking in the wrong place. Let's look at the. Okay, so yeah, let's go ahead and look at it. So we can look at. Let's see here. So I made reference earlier to WIT. WIT is the, I think, WASM interface type. So this is what a WIT file looks like. It looks somewhat similar to like Rust types, but a little bit different. You only have hyphens in names and so on and so forth. So this is the hyperware WIT file. So this is what all hyperware processes define at base. You can add more functionality to your hyperware process. You can define an API beyond this, but this is what all of them have at minimum. And these are the types and the functions that the Hyperdrive kernel furnishes to each hyperware process. So if we look here, okay, here's what a capability is. It is a record or a struct with two elements: an issuer, so who gave this capability, and then parameters, so arbitrary JSON in the form of a string. And if we go, yeah, so okay, so here are the functions that we get from the system for capabilities management. So we can look at all of our capabilities. So we would call our underscore capabilities, and then we would get back a list, or in the case of Rust, a vec of these capability structs. So we can, in fact, query what we have.
Okay.
And this save capability is how we would like. So the way that it works is like if you wanted to grant a capability to some, your process foo wants to grant a capability to some other process bar. You would send a message foo to bar. You would have presumably some messaging protocol defined where bar receives this message. Maybe the message is like, I'm giving you a capability. Then attached to that message would be the capability, and then bar could call save capabilities in order to sort of load those capabilities into bar's process state. Okay, that's another sidebar, but yeah, this hyperware WIT file is another important part of the system, and we'll see where these different host provided functions, or Hyperdrive provided functions live in just a moment here. Okay, any other questions before we... Actually, we'll go look at those next. So any other questions before we do that?
I have a question unrelated to any of this.
Sure.
Sorry. I was working on this right side screen recently
Oh,
because I
by
think.
the way, before you continue, this is being recorded, so just so you're aware.
Okay. Well, I can get you later then.
Okay.
I'm ahead.
Okay. Yeah. No worries. Just wanted to let you know. Okay. Cool. Okay. Yeah. I'll get you back on that in a little bit. Okay. Other questions, hyperdrive related. Okay. So let's take a look at where these functions are defined. So these are in WASM component terminology. These are host provided functions. So in this case, the host is the runtime, the kernel runtime module, and the guest is the WASM component or the hyperware process. So the guest gets all these functions, and then when it calls these functions, they will be executed by the kernel. So let's go look at where these are defined. So if we look in the kernel, we're going to see, right, we had these three things: mod, process, and standard host. So let's go look at standard host. So standard host is where we define these various functions. So we have a variety of helpers, but then we also have the functions that are actually exposed to. So like, for example, we were looking at okay, so our is an example. Our just returns what is our node address, or sorry, what it. Okay, so there's the node name. We didn't even talk about this, but an important aspect of the system is that each node has an identity. That identity lives on chain, and your node is going to be able to sign as that identity. So everybody knows, that, everybody can confirm that, I am nick.hyper because every message that I send to you is signed by nick.hyper's networking keys. The node identity is one part of the address. The address is that thing that I was talking about earlier, which is like the fully specified process address. So, for example, if I'm running a package foo, which has a process bar in it, and it's published by nick.hyper, and it's running on a node diligence.os, diligence.os at, oh man, I forgot, at bar, I think is the process, colon, foo is the package, colon, nick.hyper is the publisher. So our just gives you what is our process address. But yeah, so each of these things is defined, is just defining like this, it's defining what is declared in this hyperware.wit file. So we could go and look at, like, for example, our capabilities. Our capabilities is defined here. So what we're doing when we ask for our capabilities is we go and message the capabilities oracle, and we say get all, right? So then the capabilities oracle is going to have defined, what happens when I get all. Well, let's go actually look at it. Get all. So our caps oracle, when we receive a get all, will send on. So you send, right? You send the get all, and you also send a one-shot channel. So how to reply to me, right? So that's this TX, the sender, and then RX is the receiver of this one-shot channel. So we send the sender of that channel over to the capabilities oracle, and then the capabilities oracle receives that, and then on here is the process that is making the request. Right. In our case, that is our, right? Our address, and then we are going to send back from the process map all of the capabilities associated with with that process. So
I think I've seen that in the event loop. You were talking about the one-shot channels.
mhm.
There'll often be some sort of unique identifier then uh, prepended or appended. I can't remember to something that looks like an address.
Maybe let me I'm not let me see. Let's go and look at the event loop, and you can tell me if
Yeah.
so. Oops. So like you can start. I'm not going to go into like Kit stuff too much, but Kit is a tool. There's discussion elsewhere of like the repo itself, but Kit has a variety of tools packaged with it. One of which I'm going to use right now, is boot fake node, or KitF for short. So you can boot a
Uh-huh.
node that is not connected to the HyperNet, but is just like for testing offline. Fake nodes can talk to each other, which is pretty cool, but they can't talk to the network itself. So if I do KitF, looks like I already have port 8081 occupied, so I'll do -P 8081 to run the node, the fake node on 8081. But then I can do so what I'm doing to toggle this verbose mode is I'm doing Control V, or I guess maybe it's Command V for you Mac OS users. You'll have to figure that out yourself. But anyways, you can press Control V and toggle through these different verbosity modes. And now I can do things like, I'm going to go over here to, let's install an app, and then see what happens on the event loop on the right. So if I go to, I don't know, let's say like wife note. And then another thing that Kit can do is it can start packages. It can also build packages with Kit B or Kit build, Kit S or Kit start package, send it to port 8081. So what's going to happen here is I already built wife node in the past. So it's going to, what Kit is going to do is it's going to look in this pkg directory. It's going to put that into a zip file. It's going to send that to fake.os using fake.os's HTTP RPC, which I can talk more about if there's interest. And then it will send a message to App Store saying install this thing. So if I do Kit S, we see a bunch of stuff here. So let's see what all got printed out. So full event loop means every single message that happens as a result of whatever is going on the node gets printed. So you can see it is kind of a lot. It's not very useful unless you're trying to like debug stuff at a low level. So okay, HTTP server request for RPC distro sys message. So this is how Kit S is talking from the outside world to the node, is through this RPC distro sys. HTTP server is passing on RPC message to main app store sys. And now this is what a message looks like. It has a unique ID. It has a source. So where is the message coming from? HTTP server distro sys, which is kind of, the runtime module that is managing kind of the connection to the outside world through HTTP. The target of the message, which is specified by Kit, by that Kit S call, is sys, the publisher, app store, the package, main, the process, and then fake.os, that's this node itself. And then we have RSVP, so where should a reply be routed to? And then the message content itself is this request. So this request, or a similar thing to this request, is what the process is actually going to see. The process can also do things like ask for the source, or ask for this blob. Blob is an additional sort of body that you can send with a request. But here, the content of the request is new package. So we're going to create a new package. It's, and then various parameters, like what is the package name? It's wife note. What is the publisher? It's nick.hyper. And then the blob is going to contain that zip file of like the actual package content.
Okay, the RSVP handles that sort of indirect, not indirect node as an indirect node, but I mean like the not like A to B, B to C, C back to B, B to A. It allows that sort of C to A response.
Yeah. So
If not, right, you wouldn't need anything other than source and target because everything would be pairs.
yeah. Good question. I think we're getting again to the edge of my knowledge off the top of my head. I think. I mean, we can go and look at the code. I think probably we will not do that for this video, but
Okay.
the code is so right. There's a couple things going on here. There's the expects response, which is if it's not none, then we are expecting to receive a response back from the target, and we have a 15-second timeout. The RSVP, yeah, I think I think it's treated differently in different cases, but I can't tell you off the top of my head. Like if this expects response was none and an RSVP's field was still here, then a response would go to that RSVP directly. I think I think it's like trivially like if there is an expects response, then yeah, just go to the RSVP. But I'd have to look. I'd have to double check that. Do you see? So you were asking about a capabilities thing. Are you seeing any of that here, or it's something else?
Or sorry, it was about the sort of one-time channel sort of thing. And no, I'm not seeing it here
Okay.
because it's in as we scroll down, perhaps I'll see it. But right now, all the source and targets are, yeah, I mean they're basically the address that you described. They all have source and then the
Oh,
process package publisher.
I think I know what you're talking about. Sometimes you'll see just like a number, like the process will be a number.
Or addition, yeah, or maybe I don't, maybe it's additionally a number. I guess I'm not sure where the number factors in, but it was in there somewhere.
Okay, let me.
And I think I saw this like maybe with terminal processes
Yep.
and stuff.
Yep. Okay, so yeah, that's good to talk about. So, a right a an address is publisher package, process, and then node that it's running on. The process, if it's not you don't have to specify a process name. So for example, for scripts, like the terminal scripts, like you're saying, a process name is usually not specified, and then it's just given a random number.
Oh, okay. So yes. Okay. So yeah, not implicated with the channel thing that I was
Yeah.
that I thought it might be.
But here
But
you can see some caps stuff happening, right? So caps has, does App Store have VFS root? Because I guess, yeah, so we're doing a create drive here. So main App Store is trying to create a drive here, and it's trying to create a drive that is not in, App Store sys. It's trying to create it somewhere else. Normally you cannot do that, but we're checking, does App Store sys have root on VFS? In this case it does, so it's allowed to do that.
are capabilities checked on a per request basis, or are they cached once determined?
Per request, there's no caching.
Got it.
Okay, let me see. Yeah, let's see if
And
we
good.
can scroll through and find a non-process name in this, or else I'll do a terminal just to confirm that what you have seen is what I think it is. Do you have any other questions while I'm scrolling through here?
No.
Okay. Yeah, let's just do a
And
terminal.
and I'm almost positive that what you've described is going to be what it is.
Okay. So if we do net diagnostics, let's see, where's our message? Yeah. Okay. So this type of thing.
Hey, there we
Yeah.
are.
Okay. Yep. Yeah. So that's in this case, we call net diagnostics. Normally, we would have a script specified with a triplet. Like it would be like net diagnostics : terminal : sys. But you can alias them. So this one's aliased by default. So what we're doing here is we're saying the terminal gets a request. It's just net diagnostics. The terminal goes and reads Scripts JSON. Scripts JSON is similar to manifest JSON. Manifest JSON, you will remember, is where we define what processes start when a package is started. Scripts JSON is just like what scripts are included in this. And a script is just a short-lived process that you can call from the command line.
Yep. And the I know the aliasing that you can do. I know that's actually a script itself, right? To be able to alias
That's right.
other scripts.
Yep. Its processes all the way down.
What's the duration of that? Is that for as long as it's running, or is it persisted in some way between runs, or?
Good question. It's certainly as long as it's running. It might be persisted between runs. Let's go look. So we'll come back to source kernel, but let's go take a look. Let's go poke around in so Hyperdrive's packages terminal. So terminal defines, right? So I told you there's in a package there are special directories like pkg. Pkg is always in a package. You optionally have a UI. Terminal does not have a UI. Packages also have a metadata.json as a requirement. And so if we look in, let's see, alias is what we were talking about. Alias is in this case, it's a Rust program. It doesn't need to be Rust, although we mainly support Rust. We have in the past experimented with using other languages that compile to WASM components, such as Python, JavaScript, Golang. I don't think we did C, but it's possible. We did Java. Rust is the main one we support. But anyways, so this is just a Rust program. We can look at the source code. And so here is the definition of the alias terminal process. And what do we do here? We, okay, so we get the args, right? Alias, and so this is like, what is that? Can the alias name be? What is the process name that we are aliasing it to? Then we
said it's all there.
Yeah, edit alias. Okay, so terminal request edit alias. So let's go look at the terminal process. So going back to the terminal package, now let's go to the terminal process, and we're going to look for edit alias. Edit alias. Now there's a weird thing to note here, which is that there is both a terminal process and a terminal runtime module. This is very unusual. Usually it's one or the other. But in this case, it looks like edit alias is handled in the process. Okay, so what are we doing? We are handling alias change, and then we're responding. Okay, so what does handle alias change do? Handle alias change does, we parse it. Okay, we insert into state. Okay, so then the question is state preserved? Set state. Yes, state is preserved. So what's happening here is we have this state struct. We can go look at the specifics of what that state struct is, and we'll do that in a second. But the set state, this is one of the functions that we get from our WIT file. So I'm going to click over to our WIT file. Set state. This will save our state. It will persist our state between sessions, and then we would call a get state to get it out of that. And what it specifically is doing, it is using the state runtime module in order to preserve our state. So if we look at, sorry, wrong tab. If we look at here, presumably we would get state when this thing starts. We do not get state. That is surprising. Maybe that's a bug. Get typed state. Oh, okay. Okay, so get typed state is a wraparound get state. My apologies. Get typed state is from process lib. It's just wraps the get state function. And so then we set up our state. We can look at our version state thing, versioned state. Where is that defined? Terminal state v1. So terminal state v1, it has hour, and then it has our aliases, which is just a hash map of alias to process ID, and it is, as I said, preserved by set state when you do that edit.
Very cool. Now I can get my terminal set up all exactly the way I want it. No, it'll stay that way.
Yeah, it seems like, yeah. So there's an open issue for make terminal good. I think it's not bad right now, but it is, you could imagine a bash level, maybe not bash level, a close to bash level terminal experience, tabbed autocomplete, there's a lot of room for improvement. So definitely one possible interesting avenue to take. Okay, so that's let's see. I feel like that was a caveat on. We were looking at the full event loop. That's what we were looking at. Yes, and seeing capabilities, seeing what the events look like, and so on. Okay, what else should we cover here while we're here? I showed you how we define these sort of host-provided functions. Of interest might be await message. Maybe it's not called await message. What is it called? Next message, maybe. Await, send response, receive. Okay, receive. Ingest next message when it arrives along with its source. So basically this is how a process will get messages that have been given to it by the event loop. So you can think of the event loop as I said, like basically just spinning as fast as possible, taking messages and then putting them in the proper mailbox. And then the process, it can check its mailbox with receive. And you would do, for example, a loop over receive. Or, I mean, in practice, like these functions tends to be abstracted away. But that's ultimately how the process gets a message in from the kernel, is it would call this receive function. And then similarly, to send a message, you would do, for example, send request or send response.
Hold on, let me make sure I got this right.
Sure.
Okay, so the event loop itself doesn't send messages to processes. It just holds them so that the processes can themselves loop and receive them.
Yeah, that's right. So what actually happens mechanically? Let's look at this. So a process sender is a process message sender. So we can go and look at that type. This type lives over in libsource kernel. Process message sender is a sender part of a Tokyo Sync MPSC that sends or that passes kernel messages. And why am I looking at this? I'm looking at this because, okay, sorry, I'm jumping around here, but process channel capacity is 100. So what's going to happen is the event loop. So each process, when it's instantiated, has this user space process sender. So if we can go and look at, I think it's going to be process handles. No, it's going to be no, it's senders. Yeah, senders right above. So senders is what we're going to go and consult whenever we have a message to a specific process. We're going to say, do we have it in our senders? Okay. So here, for example, here's start process. We insert to senders a new channel, sends to process, and then the event loop. So the event loop is going to then, go and, like, when it gets a message, it's going to send it on that channel. And then, so let's go look at the event loop where this thing happens. Yeah, okay. So here, we receive in the event loop a message. We okay, this is all capability stuff. Capability, blah, 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 blah. Okay. This is, so now if it's not a kernel message, then we get the sender from this sender's map, and then here's the user space sender that we're unpacking. We do a dot send to put that message to that process. Now we have to go look for the receiver, right? Where does the receiver go? The receiver, let me look here at standard host. The receiver, so I think it was called receive. The function was called receive. Let's go look at what receive is doing. Okay, so receive is calling get next message for process. Okay, get next message for process is defined here in the same file. Get next message for process. Okay. We have this message queue. Ingest message. Okay, so this is getting kind of a little bit into the weeds. But if there's no message queue, right? So if the message queue is empty, and we can, I think it's getting into the weeds, so let's not delve into the message queue at this point. But ingest message is what is going to, I think, if we're at the end of the chain, actually read from the, receive and process. So the process has in its state this receiver, and this is what we are going to, this is what we ultimately call when we call that receive, right? Receive, no queue, then call ingest message, call this receive and process. So, okay, so like let's step back again. Maybe I can draw it.
Yeah, one thing I'm seeing is that you definitely seem to have meant it when you were talking about the event loop, then just taking the messages and then moving them over to their to their own new little the new inboxes that they're going to be.
That's right.
They're going to be pulled from. Is that true for processes only, or do the modules kind of work in the same way, or instead are they like invoked directly? Maybe certain functions on them being invoked directly.
It is much the same for the event loop handing it to the runtime module. It is different in how it is handled. So here I showed just a moment ago. I showed you right. You would call in the process. You would call receive, which ultimately is listening to this receiver of the channel. For a let's go look at VFS, for example. So if I go to Hyperdrive source, I'm second guessing whether VFS is the right one to look at. Let's look at VFS, sure. So if we look at VFS, right, this is the entry point VFS, and we do a bunch of stuff, and then we have this channel that was passed in as an argument, right? Receive from loop, and then we just in a loop, receive from loop. So there's more kind of layers over it in the process case, but at the end of the day, it's always the event loop puts the message on a channel, and then the process handles it in a loop for a long-lived process or a long-lived runtime module.
Very cool. As far as this is a little bit outside of this, but just because it was mentioned earlier, and I wanted to understand it within the context of the message processing, any signature checking, is that only done for things where net is implicated? Like you bypass that for all local intra-process and intermodule communication?
Yes. So, yeah, that's correct. So there's a handshake that happens in net. I'm going to be very high level for net, but there's a handshake that happens in net, and then there's some sort of like long-lived connection there that gives you some confidence that, and I think you still encrypt, right? I think it's the standard like, I don't know what the term is for it, but like, you do like the public key, private key handshake, and then you agree on like a easier, like a small, like a cheaper compute
Oh yeah, yeah.
encryption method, right?
You negotiate some sort of shared secret
That's
over
right.
over that process.
Yeah. So yeah, that happens only over net, and then on the locally, it's basically like the kernel provides these guarantees. Now if you're running a custom kernel, all bets are off, right? But if you're running a kernel from us, then we provide these guarantees that you're not going to get a spoofed message from a local process that is not actually that not actually the process that it claims to be.
Right.
Okay. Let's see. We've covered a lot of ground. I'm wondering if there's anything else that I should show you. Okay. Okay. So we looked a bit at the kernel. We looked a bit at, just very briefly, at VFS. We looked a bit at some packages. Maybe it's worth, oops. Okay, go back to Hyperdrive source. I mean, so maybe it's worth looking very briefly at net, and then we can call it a day, because I think this is going pretty long. But or we can answer questions. Okay, yeah. So net and ETH are two pretty core things, right? ETH is how we read and write to and from the chain. Read from. Anyways, and then net is the actual like peer-to-peer networking. So this code I'm relatively unfamiliar with. I was not involved in the development of it, but it's quite solid code. And right, so this is just a runtime module like any other. The entry point is networking, and you do a sort of kind of a standard handle messages from the kernel, and then it's just all about like maintaining WebSocket or TCP connections to other nodes. Yeah, I guess probably I don't want to go too much more into detail here. Now, I will say that it's been designed in such a way that we could add other connection types. I don't know, maybe UDP or something. I think web transport was another one that was proposed to be added. But right now we support TCP and WebSocket, and yeah, I guess that's all I'll say about that for now. Is there anything that you were wondering that was not addressed, or other things that you want to talk about, or questions that you still have? Now would be the time to discuss.
Yeah, and maybe this will wind up going into some sort of separate session or topic or something. I guess one quick one is just for the SQLite module and everything. Is that used by the node itself in any sense, or is it strictly in accordance for other processes that want to be able to use relational database storage?
It is not used by the node itself, although it is used by the App Store. So
okay.
So I think if you look in here, this is probably the most. I'm not sure exactly where you'll see it. Maybe here, maybe in state, but in the App Store process. No.
I know when we're setting some stuff, I had to clear out some SQLite stuff.
Yeah, I don't know off the top of my head where it is, but if you search in the App Store package, you will find I think probably the most extensive use of SQLite that we have in any packages. As far as like maybe to go a little bit further answering your question, so I referred briefly to being able to set state or get state. So this state.rs is a runtime module that is responsible for managing that state, and this uses a key value store. I can't remember the name off the top of my head, but if you build the runtime, you'll see it takes forever to build a certain library.
Is that RocksDB?
Yeah, there you go. Yep.
Okay.
Yep. So that's what's used under the hood for this state management. Okay. Other questions?
That's a lot of work for a key value pair storage system. Okay, so for let's see, it's downloads, PKG, and temp. Are those the only reserved? I mean, are they reserved names for those drives? Like you'll error out if you try to create one of them as a drive.
Downloads is not. Downloads was just App Store specific. I think it's PKG and temp, and then I think you will frequently have logs. So I think the default drive for logging is logs. UI is a common one. So if I would not be surprised if you made a UI drive for a package that did not actually serve a UI from it, if things went weird. So I think off the top of my head, the special ones that I can think of are PKG, TMP, UI, and logs.
Is temp meant to actually behave in temp in the sense that like the contents may be cleared at some future point without ceremony, or what makes it
I don't
temp?
think so. Probably it should be removed. Probably it should be removed. I think so. Yeah, I think it should probably be removed. It was added some time ago for a specific use case that never actually ended up being used. So probably it should just be removed.
Okay. I mean, the last thing is the most general, which is which will probably not be able to be answered off the top. But just like, yeah, I'm curious to understand. Given that everything isn't done through, like the whole kind of Urbit, state modification, event processing, state modification, sort of, eternal persistence approach to things, it does make me wonder where data does live then, and what its, how long its life cycle actually is, and which things are meant to be durable, which things are, and what structures are they stored in. I obviously now know a little bit more about RocksDB being the thing that's responsible for the official state of the node, and I'm assuming all the packages and probably some of the modules themselves have their own state stuff in them. I guess we saw a terminal that did, although I don't know whether or not to consider that a package or a module, given the dual nature that you described. And then like what things are truly, if you yank the power cord, then that is gone and it won't be there when you start the thing up again.
Yeah. Okay, so
it might be a highly contingent answer where it's like just a list, and here's the ones that are in this category, and here's the ones that are in that category, and just. But no, I mean, if there's a principle behind it, that would be good to know.
Yeah, there's definitely a principle. I mean, so just to address like the specific question about terminal, yeah. So we looked at the terminal process, but there is also a terminal runtime module, just because I/O tends to be runtime modules.
Okay.
But to answer,
and do the runtime modules store state as well in the same way?
think the answer is generally no. So like, as far as yeah, so I think the answer is generally no, but right. So like, let's take some specific examples. So VFS, right, does not store much state, but it does write to the disk. Like SQLite, similarly. And then if we look at like, I don't know, what's another example? So like ETH. ETH similarly does not store state, but it will read from a specific file on disk. So you can configure your RPC providers by editing that file or by giving command line arguments, for example. So these things tend to preserve state on disk, if at all. As far as like user space goes, the way to think about it is that you have like all of your variables and stuff are in memory, and the way that we have the way that we advise people to write processes and the way that we write processes ourselves is that you can think about like pulling the plug and restarting the same as the process is killed and restarted. So like if you look at the structure of a process, let's look at what's a good one to look at? App Store's pretty complicated, so I don't really want to go into that one.
I mean, as contacts have a case where certain things are, they're in the process of being edited or something, but they're not actually persisted until
Yeah, I mean, so let's
they're
say
written to state.
yeah, so let's say that you so generally the pattern is well, we can look at terminal. I think terminal had that example. Terminal. So this is the terminal process. Let's look at the alias case. I forget what it was called, set alias or something. Let's find the case here. Handle alias change. So so you receive a alias message, and then you walk through some code, and then you change the state in memory, right? So that's what's happening here on line 426, is we're changing the state in memory. And then once we're done with this code block at 420 to 439, then we do the set state call. So let's say the power goes out between execution of line 426 and 440. State has not been preserved. Once 440 is done, state has been preserved. And then when we restart, now the application will load in that alias correctly. So so there is a sort of lack of atomicity here, but the way to think about it is just, yeah, you have memory, right? So that's all your intuition for memory holds there, right? It's if the power goes out, it's gone, and then
It's volatile.
exactly.
It's volatile and it's fast.
Yep, exactly. And then you have the option as the writer of a process, what sort of persistence do you want, if any? So maybe your application doesn't have any persistence, it's all memory. Maybe you use our state runtime module with set state and get state. You can write files with VFS. You can do SQLite. You can do key value. These are all different ways of persisting, and they should all be pretty reliable.
Key value is independent of the official state.
Yes, so we have state, and then we also have a key value runtime module that is exposed to that applications can make use of, and it's I should say, so I spent a little time explaining VFS drives, much the same way we have key value and SQLite databases with capabilities. So when you create a database in a process, you get read and write for that, read and write capabilities for that database, and then you can share those if you so choose with other processes, or you can just keep them in house as private databases. Yeah.
Is there any? Okay, so like SQLite and the ability to basically, given the way the multiple ways that you can query uh, relational data, that's one thing. That's one argument why you'd put something in a database.
Mm-hmm.
Is there any practical difference between keeping stuff in state or keeping it in your package's key value store?
So I think, like, let's say that you have some large piece of state, like let's say your state is like a megabyte, and you just want to access like a field within it, then probably the key value store could be valuable for that. I think one piece of work here, I said that App Store is like the main case where we've actually used SQLite. I think part of the reason that we're so quick to use get state and set state is it's like quick and easy, and maybe it's not the most efficient, but it's just like it.
Oh yeah,
Like
yeah.
in terms of it's like a function call, right? It's very easy. Whereas
Now
like,
I have my data.
that's right.
It doesn't matter how much had to be pushed, through various processes. Doesn't matter how much memory it's
Yes.
occupying.
Yeah.
Now that I'm looking at it, but it's here, and I know it. I know it's here.
That's right. That said, I think key value and SQLite have not been really like the DevX has not really been pushed that hard. So like I think they're not super usable at this point. Like you can use them, they will work, but probably there can be significant improvements to the developer experience too.
Yeah, that sort of seems like the thing that would be kind of like use driven, as like
Yep.
certain apps start getting developed to where you would want to take advantage of that, and for performance optimizations
Yep.
and stuff like that. It's like, oh, okay, well, this one part of this isn't really working very well. Okay, let's make sure to flesh out the affordance
For sure.
fully. Okay.
Yep. Okay. Any other questions?
No, that's this. I mean, my God, boy, I know a lot more about this stuff than I did coming in. Thanks to this presentation.
Yeah, I mean, hopefully this gives you a jumping off point. Like, there's a lot of details we didn't cover. I think the hyperware book is a good resource. Of course, feel free to ask questions. And I think, hopefully at least this will give you, okay, I can look here to learn more about this.
Yeah. Oh, yeah. Like right now, I'm really excited to look at the boot sequence to see more. Just also, like, first of all, just to see, like, oh, okay, hey, I remember, I know about this thing, and yep, here's where it first gets instantiated and everything, and now it's a potential target for the event loop later on. And similarly, I expect to see things like, what the hell is this? I don't know. I have no idea what's happening here.
Yeah.
And then see if I can, kind of use parallel construction to figure my way into it.
Mm-hmm. Mm-hmm. Yeah. Yeah. I mean, definitely consider me a resource, and I'm glad that this was useful.